Only in math problems can you buy 60 cantaloupes and no one asks what the hell is wrong with you. Good little Peanuts comic there. I'm sure many of you feel this way at times with some of our application problems. All right, now this section is one of my favorites. It's properties of logarithms. And these in my mind are just kind of like big puzzles. They're fun, but you guys know I think math is fun all the time anyway. But hopefully you'll get a little enjoyment out of them as well. So we have 7 basic properties of logarithms, and we've got to learn those properties first, some of which we've actually already seen, and then we're going to be able to apply these to logarithmic expressions to do some rearranging, which is then going to set us up for what we're going to look at in the future, which is solving logarithmic equations. So, first property, we have log base a of x plus log base a of y equals log base a of x times y. So realize that in order for this property to work, my bases must be the same. And then when I'm adding 2 logarithms that have the same base, I'm able to squish them down into one logarithm by multiplying their arguments. So xy really means x times y. Okay. Now, very similarly, we have a rule like that works with subtraction. If I am subtracting 2 logarithms that have the same base, so log base a of x minus log base a of y, I can squish it down into one logarithm still with that same base, but now instead those 2 logarithms being subtracted are squished down into one logarithm where those arguments are being divided. So 1 and 2 are similar in terms of their setup, but you've got to realize that the 2 logarithms being added squishes down into the arguments being multiplied. Those 2 logarithms being subtracted squish down into those arguments being divided. All right, now, the next rule is one of my favorite rules. It is a rule in which we have log base a of x to the n. Now, what happens here is I actually can take this exponent and bring it down to the front. And it's the same as n log base a of x. Now, realize this rule works in both directions. So if I start with n log base a of x, I can also take that number, that coefficient that's in the front, and throw it back up to that exponent position. And I would get log base a of x to the n. So that one goes in both directions. All right, now we have log base a of a equals 1. We saw this one already. Remember that when we are thinking about logarithms, this really means that a to the first equals a. So we got that one checked off our list. The next one essentially combines 3 and 4. Keep in mind that this exponent n I can bring down front. And now this would give me n log base a of a. But we know that log base a of a is equal to 1. So this would be like n times 1, which is just n. So that's what's going on behind the scenes. But here we can see the shortcut or the property is that log base a of a to the n just equals n. Rule number 6, we saw it already when we were converting between exponential and logarithmic functions. Log base a of 1 equals 0. Anything to the 0 equals 1. And the last one we have here is a to the log base a of x equals x. So essentially what happens here is that a to the log base a, their inverses, we get x. All right, so let's use these rules. First thing up, we want to combine log base 2 of p cubed plus log base 2 of q. Notice that these have the same base and they are being added. So I can combine these into a single logarithm, log base 2 of p cubed q. Okay, let's go ahead and put that p cubed q in parentheses too, so we know that's all together being multiplied. Okay, now in order for me to combine these, okay, all I had to do was squish them down into one logarithm. They didn't ask me to do anything about bringing that exponent of 3 down to the front or anything like that. So this is our answer right here. Boom. All right, now the next one they want us to express as a product. So now they're essentially asking us to bring that exponent down front. So log base a of 11 to the negative 3 is going to be the same as negative 3 times the log base a of 11. Now, on this next one, we previously learned that the square root of x was the same as x to the 1/2. This time we don't have a square root, we have a fourth root. Okay, that's going to be the same as an exponent of 1/4. Okay, so remember with the square root, they don't write it, but it's got that invisible index of 2. So that's where that exponent of 1/2 comes from. With the fourth root of x, we can see that index and our exponent is going to be 1/4. Now, that's just generically over there on the right. In this particular problem, we have the ln of the fourth root of 7. So this is the same as the ln of 7 to the 1/4. Now we can bring that exponent down front. Whee! And we get 1/4 ln of 7. This is now a product because it's really 1/4 times the ln of 7. So that's where those directions come from in terms of expressing it as a product. When we bring that exponent down front, it's connected with multiplication. All right, next one, we want to write this as a difference of logarithms. So notice this one is already condensed into a single logarithm, but I have my two arguments being divided. So I'm going to break this apart into log base t of 8 minus log base t of w. So it gets broken apart into two separate logarithms being subtracted. And remember that that base has to be the same all the way through. All right, now we're going to write as a single logarithm, and we need to fully simplify our answer for log base 8 of 32 minus log base 8 of 4. Now, to start out with, notice that these bases are the same. And my two logarithms are being subtracted. So I am going to combine these into a single logarithm as log base 8 of 32 over 4. So those arguments get divided. But 32 over 4, I can reduce as a fraction. That's actually equal to 8. So this is log base 8 of 8. What do we know when the base and the argument are the same? Log base 8 of 8 is going to simply equal 1. Boom. All that simplifies just down into the number 1. All right, now this one we've got sum and difference of logarithms going on. It says write as a sum and difference of logarithms, simplifying your answers completely. Okay, so if we look at this argument, I'm going to put parentheses around there to kind of get us to focus on it. You can see in the numerator that I have x squared times y to the 5th. And then in the denominator, I've got divided by w to the 4th. So when I break this apart, x squared and y to the 5th are currently connected by multiplication. When they separate, they're going to be connected by addition. My w to the fourth is currently connected by division. Sorry, w to the fourth is connected by that division because it's in the denominator of my fraction. So when I break these apart into separate logarithms, that argument is going to end up being a logarithm that is subtracted. So check out what I end up with here. I have log base a of x squared plus log base a of y to the fifth minus log base a of w to the fourth. Notice that that base stayed the same all the way through. I can go one step further with this one. We can bring each of these exponents down to the front. Whee! It's like a little slide. So we end up with 2 log base a of x plus 5 log base a of y minus 4 log base a of w. There we go. So we had 3 separate rules that we ended up using on this one. Now, we just recently discussed that the square root of x was the same as x to the 1/4, and that the fourth root of x, nope, rewind for me. Beep, beep, beep. I'm getting ahead of myself in my brain. The square root of x is the same as x to the 1/2. We said that the fourth root of x was equal to x to the 1/4. What do you think the cube root of x is equal to? Yeah, exactly. It's x to the 1/3. So we've got to keep that in mind on this particular problem because we have log base a of the cube root of this a squared times b over c to the fifth. So let's start out by rewriting that cube root as an exponent of 1/3. So we are going to end up with log base a of a squared b over c to the fifth all to the 1/3. Okay. Now, at this point, we do have a couple options. We could go back to our exponent properties and think about the fact that that 1/3 belongs to everything inside the parentheses. Or we can go back to that new log property we've learned where we can take this 1/3 and bring it down to the front. What we have to remember, though, if we choose to do that, is that 1/3 still belongs to everything that's behind it that still hasn't been separated. Okay. Now, if I leave that 1/3 in the front, don't forget about it, okay? We now have log base a of a squared b over c to the fifth. And this actually becomes very similar to the previous problem we just did. A squared and b are connected by multiplication in the numerator, and that c to the fifth is connected by division in the denominator. So if I break apart that multiplication, I'm going to have 2 logarithms being added. And if I break apart that division, I'm going to have the logarithm being subtracted. So we now are going to have the following. We have 1/3, keep it in the front, times log base a of a squared plus log base a of b plus log base a of c to the fifth. Let me just remind you, too, that as you're writing these logarithms, remember that that base is always written in the subscript as opposed to in line with the argument. Okay. All right. We can bring some exponents down front here. We've got a 2 we can bring down front. We've got a 5 we can bring down front. So we would have 1/3 times 2 log base a of a plus log base a of b plus 5 log base a of c. What do we know about log base a of a? Yeah, it's equal to 1. And 2 times 1 is just going to leave me with a 2. So I have 1/3 times 2 plus log base a of b plus 5 log base a of c. Now, I used brackets here on the outside just to differentiate from my parentheses that I previously had around a squared b over c to the 5th. Parentheses here would also be perfectly acceptable. One last thing that I could do is I could distribute this 1/3 through. Just kind of depends on how far an answer wants you to go. And I would get 2/3 plus 1/3 log base a of b plus 5/3, I'm going to see if I can squeeze it in here, log base a of c. There we go. All right. This time, rather than separating the logarithm out, they're giving us the separate logarithms, and we want to squish it back into a single one, okay? Now, to start out here, notice that I have some numbers or coefficients in the front of each term. I've got a 5 and a 1/4. In both of those cases, I can throw them up. Whoop. So I can right off the bat rewrite this as log base b of x to the 5th minus log base b of y plus log base b of z to the 1/4. Now, keep in mind, the reason I'm going to be able to combine these into a single logarithm is because they all have the same base to begin with. Now, my x to the 5th, my log base b of x to the 5th is connected to log base b of y right now by being subtracted. Okay, so if we kind of work our way across left to right, okay, and I just combine those first two terms to begin with, I would have log base b of x to the 5th over y. Okay, now I still have plus log base b of z to the 1/4. Now, these two logarithms, still with the same base b, are connected by addition. So the way I'm going to combine these now down into a single logarithm is I'm going to multiply them. So that z to the 1/4 is going to hang out in the numerator with the x to the 5th. So I'm going to have log base b of x to the 5th z to the 1/4 over y. And that would be my final answer. Now, depending on your comfort level, once you've done some more of these, you might even go back to that initial problem and see, okay, x to the 5th and z to the 1/4, they're going to stay in the top, and then that y is going to go to the bottom. So you can pay attention to those signs that are in front of each term to make that decision, or you can just work small pieces left to right going across, and that will absolutely work as well. All right, let me stop there for now, and we'll come back with part 2.